So, today we are going to discuss the bail opening machines. Now, the name of the machine is bail breaker or bail opener. It is a very traditional machine. The diagram is shown on the left hand side, and this is a cross sectional view of the machine. And if we look at the structural feature of the machine, then what we see is there is a feed lattice over here and there is a horizontal lattice. And then third, there is a vertical lattice called inclined spike lattice, and this lattice is inclined. It is not really perfectly perpendicular with respect to the floor. Then there is a reserve box. There is a box where the treated tufts will be accumulating. There are two rollers which you can see here. One is called the Evener roller and the other one is called as Doffer roller, or it is also known as stripper roller. The opening zone here exists in between the Evener roller and the spike lattice. The density of the spikes is around 21 per feet square. That is, this cross sectional view that you see of the spike, it is just like a conveyor with a large number of spikes on it. So, per meter square it will come around 233. The spikes has a diameter around 6 to 7 mm and they are very strong because they have to always act on entangled tufts of fibers. Their opening intensity is generally mild, or we can say quite gentle in nature. So, this is the description part of the equipment which is used to open the compact mass of fibers from the bail. If you try to understand the working principle of the machine, which is like this, that the what we do here, that at the input we feed large chunk of tufts from bales. So, from the bale, first of all these chunks of materials are peeled off and they are dumped on the feed lattice, on this lattice. The feed lattice which is moving will deliver the material on the horizontal lattice. So, feed lattice it is outside the machine, while the horizontal lattice is inside the machine. The accumulated tufts, as you keep on feeding the tufts inside the machine, the tufts will come and accumulate here, and gradually a large mass of tuft will accumulate there. The mass of tufts will be lifted up because the spike lattice is going to penetrate the tufts, because it is moving up. So, this will also take the tufts along with it, and the tufts will come where it will reach the interacting zone which is here. Now, as soon as the tufts are brought here, where the Evener rollers strikers are also acting. The Evener rollers, if you look at it, it is revolving in the opposite directions. That means, at the interacting zone, the spikes are moving in one direction and the striking elements of the Evener roller is moving in the opposite directions. and the gap between them is quite narrow. So, as a result what will happen? The tufts is going to be acted by two opposing set of spikes which are moving in two opposite directions. So, some tufts which are not held securely by the spikes may roll down as they are lifted, and some of them will reach the interacting zone and will receive a blow from the spikes of the ulnar roller. So, as a result of this blow, what is going to happen? The tuft will be sheared into pieces, and one part which is not attached to the spikes will be falling back into the beam. The other part will move forward. That means, a large part, a large tuft will be broken into pieces, and the smaller piece will be able to pass through the interacting zone, and the other piece which is not held by the spikes now will be thrown back into the beam part of the machine. Once it crosses this zone, what happens? Now, there is a roller over here, that is the Doepfer roller, or we can say it stripper roller. So, what it is doing? This stripper roller or the Doepfer roller will remove the tufts from the spikes of the inclined spike lattice. Its job is to remove the tufts from the, its rotational direction will be like this, in the, it should rotate in the clockwise direction always, and it will be able to strip the surface of the inclined spike lattice, and those tufts will move forward and then it will fall in the reserve box as shown in the diagram. Now, while dumping cotton tufts on the feed lattice, normally what happens that if we dump in a manner as shown here, that the middle part is quite thick and the both sides the thickness is less and less. If we dump in this manner, this is not the right way of dumping material on the feed lattice, because this will affect the amount of feed by the feed lattice on the horizontal lattice. So, a better approach is to have a situation like this, where this unevenness part is much less. So, we have to ensure that if we are dumping material on the feed lattice, the height of the material on the feed lattice is as uniform as possible. Something like this is not really good, whereas the one shown at the bottom is the right way of dumping. While dumping, we have to try to spread out the material on the feed lattice, so that the material which is fed by the feed lattice remains more or less constant. This is how the machine is going to work. So, there is always a store of material inside this machine, and this store of material could be it may, that could be the space here may be filled up to the extent of half or 50% or maybe sometimes 3/4 may be occupied by the tufts. Now, in this diagram what we see here, a a photograph which shows how the inclined spike lattice is filled with tufts of varying sizes. The other thing about this machine is that there is a swing door over here as shown in this diagram, no swing door. So, there is actually a rod which is hinged over here and the rod can swing in this direction. So, a swinging action depends upon the volume of material that we have inside the bean. If the bean is filled to the extent of 3/4, the door will swing on the left hand side, and as a result what happens? The swinging action of the door will send a signal to a motor, and as a result the feed lattice will stop its movement. So, we can stop the movement of the feed lattice once this part of the machine is filled with large volume of tufts. So, this is how the machine is going to work. The tumbling action which is continuously going on inside the machine will cause lot of dust to be liberated also. So, because right now there is not much cleaning, so that we are continuously the tufts are moving up, some of them are falling back, the horizontal lattice is moving forward. So, there is a continuous tumbling action which is going on, and as a result a lot of dust will be liberated and the space within the machine will be filled with dusty air. So, we can also remove dust from the machine right now. So, we can connect the machine with a suction fan, and with a controlled suction we will be able to remove some dust which is getting generated because of the tumbling action. So, it can be sucked off. Now, we will just discuss about the significance of inclination of the inclined spike lattice. We see the diagram over here that the spike lattice usually it is the angle is obtuse, but let us say what will happen if the angle is right angle or acute angle. There are two things that is important here. One is let us look at it from the mixing possibility. There are large number of tufts within the machine, and the entire mass of tufts within the machine is continuously rolling, because the feed lattice is moving and the inclined spike lattice is moving. So, this mass of material is in a rolling state, and therefore, there is a chance of mixing of the tufts. So, that possibility is there always, that within the machine the tufts have an opportunity to be continuously mixing with each other. But this rolling action that may happen can also lead to NEPS generation. So, too much of rolling is not good, that also to remember that it can lead to formation of NEPS. Now, other aspect is loading of the tufts. More tufts will slip off, the inclination angle is acute. Let us say here, if we think of a situation like this, lot of tufts will fall down because of the gravity action. The force which will be acting on it, the component which is acting away from the spike will be more, and hence more and more tufts will fall down. That possibility is there. The tuft loading on the ISL will be more when the inclination angle is obtuse. So, if the angle is obtuse, obviously more and more tufts will be carried forward. So, for we have to think of a certain level of production, and therefore, we have to see that there is a right amount of loading of the spiked lattice, and that loading factor depends upon the inclination angle of the spike lattice. So, a right angle or an acute angle will reduce the loading of the spike lattice, and in a way in that case the production rate also could be affected. And hence, what is normally done by all the machine manufacturers is that the spike lattice is inclined with respect to the horizontal lattice, and that angle is usually an obtuse angle. The intensity of the opening action here. First of all, the opening action is very mild, that we have already stated. The only opening zone is here as shown in this diagram. For clarity, we are only showing the spike lattice and the Ebenard roller. Okay. And what we see here is that there is a certain gap between the teeth of the Ebenard roller spikes and the spikes of the spike lattice, and let us say that gap is delta y. The length of the interacting zone, let us say as shown in the diagram, is x. Let us say this is the value x. Let the surface speed of the spike lattice is v meters per minute. The length of a typical tuft, let us say, is L, and the speed of the Ebenard roller is n rpm. So, this is n. Number of rows of spikes of the Ebenard roller is p. Okay. So, number of rows of spikes. In this case, let us say we can see there are 1, 2, 3, 4, 5, 6, 7, 8. 8 rows of spikes are there. So, p value will be 8 in this case. Time taken by a tuft to cross this zone. So, if a tuft is of length L, it has to cross a zone x. Time that the tuft will take to cross the zone will be x plus L divided by v. Now, during this time, the number of revolution of the Ebenard roller is going to be T into n, and number of beatings B a tuft will receive while crossing this zone. Beating by whom? Beating by the striking elements or the spikes of the Ebenard roller. So, how many they will receive? It will be P T n, where T is x plus L by V, and therefore, the number of beatings a tuft is likely to receive is going to be x plus L by V into P into n. Now, from here what we can say that if we increase V, that is, if I increase the speed of the spike lattice, the value of B is going to go down. That means, it will reduction in opening intensity. The net result will be opening intensity is going to reduce in that case. If n is increased, if the Ebenard roller speed is going to increase, keeping rest of the things same, then B is going to increase, that will increase the opening intensity also. The other thing that can affect opening intensity is the gap delta y, which is not coming into this equation, but that can also affect the intensity of the opening. So, the production rate in this case depends upon the speed of ISL, the speed of the spike lattice. I stands for inclined, and also depends upon the spacing, which is delta y. So, if we have a large space, large tufts will be able to pass through, and therefore, they will not be obstructed by the teeth of the Evener roller. As a result, production is going to be increased, but it will be at the cost of lowering the opening intensity, because big tufts will be able to pass through. But you should know that the production rate depends upon two important factors: the speed of the ISL and the spacing delta y. Okay. So, this is the structure of the machine that we have discussed. How the machine works we have also discussed, and what are the factors which affect the opening intensity of the machine, that also we have discussed. Now, there are machines of similar type designed by different machine manufacturers. So, let us say this is another machines where what extra we see here, the extra part that we see here is this part, which was not there. This whole thing, that this vertical reserve trunk and along with this cage condenser, stripper roll, this is not there in the previous machines. So, the rest of the things is exactly same. So, there are machine manufactured who will be making machines like this. That means, I can feed some tufts from this side, and also I can feed some tufts from this side. So, in case we need to mix two different types of fibers, then this is one possibility through which we will be able to mix them and then process them together. Okay. So, that is all. Rest of the working mechanism or working principle is exactly same. The other machines of similar configuration that we see in the blow room is known as hopper feeder. So, if you look at the hopper feeder here, the diagram on the right hand side, what is the difference that we can observe? The construction part wise it is very similar to the bail opener or bail breaker that we have seen earlier. What is missing here and what is additional? One is there is no feed lattice. So, there is no long feed lattice, it is no more there. So, I mean that does not exist in this hopper feeder. And what is there is a reserved compartment or a feed trunk which is here, through which we will be feeding the tufts. And the other difference is the Evener lattice. So, there is no Evener roller. So, the roller has been replaced by also a lattice, and the lattice is having spikes on it. And there is a big reserve box in front of it. Reserve box could be also there in the previous machine. So, this is also here. So, you have a reserve box, you have a feed trunk, an Evener lattice is there. Otherwise, the constructional features of this machine, bail breaker and the previous machine is almost same. The other difference is it is much larger in size. See, the name itself says it is a feeder. That means, we want to store the material here. In the entire blow room line, there are quite a few machines which are connected to each other. So, we need also a machine where we can store the material for some time, and we will be able to feed it whenever there is a demand of material from the subsequent machines. So, because it has to store, therefore, it is larger in size. It is used to ensure steady and uniform supply of material to the opening and cleaning line. So, the reserve compartment hold the material in the main bin at a constant volume. So, this hopper will store lot of material here. Working principle wise, it is similar to the bale opener. We also get little some amount of opening actions in between the spikes of the Evenard lattice and the spike lattice. So, what are the difference between the bale breaker or bale opener and the hopper feeder? Now, it has been stated here in this particular table. So, let us first look at this spike density on the spike lattice. For the bale opener, the density is 21 per feet square. Hopper feeder, it is 69 per feet square. So, in hopper feeder, we have more number of spikes, and the spikes are smaller in diameter and shorter in length. Why? Because tufts are more open, so there will be less stress on the spikes, and tufts are also smaller in size. Because tufts are reduced, because this machine is not going to be the first machine in the line. Bale opener and bale breakers are usually the very first machine in the blow room line, and therefore, they have to always act on very tangled mass, very compressed mass of fibers, and therefore, the spikes on the spike lattice has to be very strong and sturdy, so that they do not break easily. But by this hopper feeder, though similar in constructions, but not used at the beginning of the line, it will be somewhere in between, somewhere at the middle. It is just like a storage space for us. So, by the time the material reaches here, the tufts are smaller in size and they are little bit opened also by the previous machines, and hence the spike density is much more and the spikes are also smaller in size. So, that we have more number of spikes per unit area, otherwise many tufts will simply roll down. How many spikes we will have per unit area on the spike lattice? It depends upon what is the average tuft size. If the tufts are bigger, we will have less number of spikes per unit area. When the tufts are smaller, we have to have more number of spikes per unit area. If we do not have more number of spikes per unit area, if we keep the same number of suppose spikes per unit area like bale opener, then what we will find? The smaller tufts will find space to roll down, space between the spikes. There are enough space available between the spikes in that case, and through those spaces the small tuft will simply fall down. They will not be lifted, they will not be carried forward. That is the difficulty we will face if we have a similar spike density in hopper feeder as we have in bale opener. Okay. Now, Evenard roller and Evenard lattice also we see a difference. The roller tend to form laps when waste fibers are used, so we generally replace it by a lattice. So, Evenard roller has a tendency sometimes that it has been found that it can, the spikes gets filled up with lot of tufts, and that is especially when waste is used. So, sometimes we have to mix some waste fibers along with the virgin fiber for processing, and this problem has been noticed, and to overcome this problem, if we replace the roller by a lattice, then possibilities of the rolling is less, that is the roller getting filled up with lot of fibers will not be left. If these spikes gets filled up with fibers of the Evenard roller, then the opening intensity will go down, and therefore, we have to ensure that the Ebner roller striking elements or Ebner roller spikes, whatever we say, they should not hold the fibers. Okay? And the other thing is spike lattice is short and long, we have already discussed. The long to increase the quantity of stock, because we want to keep a large volume of material within the beam, and therefore, this machine has to be larger in size. So, we increase the height of the machine, and hence we need a long spike lattice. So, these are the reasons why there is a difference. Disadvantages of the machines are spikes break and slats need frequent repair. With these machines, these problems are there. Shafts and blocks need cleaning periodically, and changing apron is also time consuming. So, whenever if there is lattice apron, lattice is nothing but basically a type of conveyor which will carry the material forward. So, if it breaks, then changing it is a very time consuming operations. So, these are the some disadvantages of with these machines, and therefore, the alternative is feed unit or a feed trunk, which could be which has been designed also, where we can store the material, and we will also see that we can also store the material in mixing equipment, which we will discuss in the when we in this course itself. The augmentation of the basic unit of bell opener and hopper feeders, that we can, you will find that we can augment the basic unit by having some attachment. So, we can have some attachment or auxiliary units, like we can deposit the treated material onto a conveyor or into a suction duct or into an weighing unit or into the opening and cleaning unit of a cleaning machines, which will be in front of it. So, the basic unit is what we have discussed, but we can have some attachment or we can have some auxiliary units depending upon the need of the line, the way we design the line. We can either have a conveyor that the material can fall onto a conveyor, or we can have a suction duct, material will be sucked out, or it can fall into a weighing unit, it falls there, and once a certain amount of tufts fall into the unit, then it will be dropped down. So, that is similar to a blender. So, that we will be discussing also later on, but it can drop into a weighing unit, or it can be directly fed to the to a cleaning machine or a cleaning equipment subsequently also. So, these auxiliary units can also be a part of the hopper feeder. Nowadays, what we have is automatic bell opening machine, which are much more efficient and which needs less maintenance, and therefore, such automatic bell opening machines are becoming more and more popular today. So, what is the general feature of these automatic bell opening machines? A travelling head extract tufts from let down bells from top to bottom. So, here the manual operation is no more there. In the earlier machines, we used to peel off the material from the bell manually and then dump it onto the feed lattice of a bell opener. But automatic bell opening machines will not have any manual operations. The only manual operation is that you have to lay down the bales on the floor near to the machine in a particular order. That is what is done. Rest is taken care of by the machine itself. So, the machine has a travelling head which extracts tuts from the laid down bales from top to bottom. So, this is one thing. The machine extracts material in batches and process the material from 1, 2, 3 bales simultaneously at a time, and therefore, we get a very good mixing of tufts in the automatic bale opening machines. And the bale layout may consist more than 100 bales from 4 to 6 types of bales per fiber blend. So, actually 4 to 6 different types of bale groups can be laid down along the machine, and the machine will be able to process all those bales together. So, that is what is the interesting part. Now, we will discuss the construction and design feature of the machine. First, there is a track which is almost 50 meter in length, on which a movable head as a turret can traverse. So, this is the turret is shown in the diagram, and these two are the rails. So, this turret consisting of this vertical box represented by, and there is a horizontal part also you see rectangular box, which is the extracting assembly. So, put together this is what can move back and forth over a rail. So, this entire head consisting of a turret, a chassis, an extracting assembly is mobile in nature, and to move it there is a rail on which this entire head will keep on moving. So, the track is actually 50 meter in length with a movable head and traverse forward and backward at around 20 meters per minute. The length of the track is long enough to accommodate up to 200 bales. So, we can accommodate 200 bales, and we can put the bales on both sides of the rail or both sides of the track. The movable head extracting assembly, it has an extracting assembly which is shown here, and which can pluck tufts from bale's top surface, and this can actually remove tufts from the bale surface. That is also important, that is we have a specially designed roller, and this roller will be able to extract the tufts from the surface of the bales, and an internal suction sucks the tufts. Once the tufts are plucked from the surface of the bale, the internal suction is there within this turret, which will be suck out the tufts and transport it to the next machine. The head can also turn by 180 degree and process bale therefore on the both sides of the track. So, while moving backward and forward, it can also turn its head by 180 degrees. So, while going or while moving in one direction and the head is on one side, suppose with respect to this diagram, the head is on the right hand side of the turret, the bales are on the right. So, any bales which are placed on the right hand side, they all will be acted now, or they will be opened out by this automatic machine, and while coming back this entire turret will turn by 180 degree, and bales kept on the left hand side now will be acted upon. This takeoff unit consists of a double tooth disc which can change its directions of rotation. We will discuss that, we will see the more detailed diagram the next. The takeoff unit can adjust itself to various bale heights by moving up and down. The entire extracting assembly that you see here, or you can call it takeoff unit, this assembly can also is self adjustable. That is, it can move up and down depending upon the height of the bale. So, the bales are coming from different locations. So, sometimes the bales are not exactly of same size. The bales may vary a little bit in terms of their length, breadth and height. There is not much standardization here. So, if we procure bales from different countries, it may vary in size, and hence this takeoff unit can really move downwards depending upon the height of the bale. It can move up and down. The various machines which are there, they are companies are Trussler or Ritter or Microflock and Bale Plucker. So, these are LMW, Hudgeth and Hollingsworth. So, these are the companies which make Ritter company or Trussler, they make these machines, and the basic principle of the work is similar in nature. We will now discuss the way the machine is going to work. So, the structural feature of the machine is shown here. This takeoff unit is here. So, this one thing is takeoff unit, the bale is here, and you see within these there are two, there is a disc. We will discuss the next diagram which is given in more details. Now, the extracting assembly or the opening and takeoff roller may be one or two with double sided tooth disc. So, this assembly that is shown it here may have how many? They may have one or two takeoff rollers with double sided tooth disc. That is what is important. That is, you can have either one single or two rollers, but all these rollers will be having double sided tooth. Whatever is the traverse direction, one roller will have working tooth disc in the direction of the traverse and the other will oppose it, because it travels back and forth. Therefore, the direction of rotation has to be changed, and if we have the tooth disc in the angles are in both the directions, then while it is coming back, the tooths which are in the opposite direction now will work on the bales. So, therefore, the discs have teeth which are oriented in two directions. The two layers of tufts are plucked in one pass with two opening rollers. The discs opposing the direction of traverse plug the very first layer, and the other disc penetrates the bale further down and plug the second layer of tufts. So, while we use two opening rollers, like in this case there are two opening rollers are there, and therefore, in this case as it travels back and forth, it will be able to remove or pluck out tufts from two different layers. If we have a single roller, then obviously it will be able to pluck out tufts from a single layer only. So, to increase the productivity, we can use two opening rollers as shown in this diagram, in the left hand side diagram. The depth of penetration is usually 2 to 4 millimeter, and the depth of penetration can be also adjusted. So, if I increase the depth of penetration, what will happen? The productivity will be more, because larger tufts will be plucked now. So, if you reduce the depth of penetration, you will be able to produce smaller tufts. So, see, if we want to produce smaller tufts, we have to reduce the depth of penetration, but that will affect my productivity. If I want to increase productivity, I have to increase the depth of penetration, but that will give me larger tufts. So, depending upon my own assessment, one has to decide what should be the right depth of penetration. There are two pressing rollers over here, you see. These pressing rollers will press the bale surface, and the opening roller as shown here will be penetrating, and as it rotates, it will keep on removing the tufts from the surface of the bell, and as soon as the tufts are plucked, they move upwards and immediately they are sucked. So, they are sucked out, and through the suction system they will be going to the main line. The bales are first lined up on both sides of the machine. The bale can be arranged lengthwise or crosswise. The lengthwise arrangement is shown here, the crosswise arrangement is shown here, and this could be a mixed type of arrangement. So, you see the lengthwise arrangement and crosswise arrangements. Bale heights are automatically detected, and the machine calculates the penetration depth and traverse speed automatically. Depending upon the productivity you want, we can set the machine, and machine will automatically decide the penetration depth and its speed. As these movable tower travels, the rotating takeoff roller plucks the tufts from the bale's top surface, which we have said already. The removed tufts are transported pneumatically to the next machine. Reaching the end of the traverse, it turns by 180 degree and start polishing the bales on the other side. Spaces to be left between the individual bale groups, so that extraction roller can adapt to the varying bale height. If at all there is a change in bale height, then there has to be some gap left between the bales, so that it gets sufficient time to sense the height, and accordingly it can come down and pick up the tufts from the bale. The machine in this zone opens the material gently and generates smallest flocks of almost equal size. That is the biggest advantage of these automatic bale pluckers or bale opening machines, that the size of the tufts may be varied between 30 to 80 mg, but the size difference is much less. In a bale opener, the tuft sizes will vary a lot, because there is not much control on the size of the tufts. So, the variability in the weight of the tufts is much more with the traditional bale opening devices, whereas this type of automatic bale opening devices, the variability in the tuft size is much less, and production rate could be to the order of 2000 kg per hour. One can say it can go up to 2000 kg per hour. Next we discuss about the bales laydown. See, there are varieties, different types of laydown which a mill can practice. Type 1, only one row. So, one row of bales with broad sides in the direction of the detaching. This is one way of placing the bales. And number 2 type, you see it is known as 1.5 row, 1.5 row of bales with a long and broad side in the direction of detaching. So, this is the figure itself is almost self explanatory. You can understand easily from the figure itself that these are the different ways we can place the bales. We can place the bale in 2 rows, one behind the other, and this is the direction of your detaching, or we can have 4 bales in a row, and like that 3 rows of bales could be there. There is another category, or that could be 4 rows of bales also be there. So, there are different ways in which the bales can be let down, because ultimately what we have to see, for a given length of the track, we have to accommodate as many bales as possible, so that we can take material from a large number of bales. If we can take material from large number of bales and can mix the tufts, then there will be consistent quality of yarn that will be produced. So, from the point of view of consistency in the quality of the final yarn, it is better to take more number of bales. Now, we will have a calculation just to know number of how many bales we could be there in a laydown. Calculation of number of bales per laydown. Let us say we take an example. The example is stated here. A spinning mill has 4 different bale groups and wishes to combine this according to the proportion given here, 20%, 10%, 50% and 20%. So, and there is a 40 meter duct length, but which makes the bales laydown length limited to 34 meter. Now, this is what is given here. So, table shows bales belonging to 4 different groups. The length of the bales and the width of the bales and the weight of the bale is stated here for group 1, 2, 3, 4. The percentage that we need in the mix is also given, and how the bales will be placed. One is crosswise placement and the other one is lengthwise placement, both could be there. So, how many bales can be accommodated in the laydown and calculate the number of bales in different groups. This is what the question is and how to go about it. First, the average length of a bale has to be determined. Now, for crosswise arrangement, the bale length will be equal to the bale width as shown in this diagram, and for lengthwise arrangement with 2 bales like shown here, the average bale length is going to be L by 2, and if we have 3 bales, then the average bale length is going to be L by 3. So, look at the way the bales are placed and why it is L by 2, because in this length L I can accommodate 2 bales. So, therefore, the average bale length is going to be L by 2. In this case, in the length L I can accommodate 1, 2, 3 bales I can accommodate, and that is why the average length is L by 3. Okay. The same table is here repeated. Now, from there, following this rule, we can find out what is the average bale width. What we should do? For bale group 1, it is a crosswise arrangement because it is cube here, and therefore, bale width is going to be exactly B. What is the value of B for this bale group? It is 0.6. So, 0.6. For bale group 2 is also crosswise and the bale width is 0.7. So, I did in 0.7. For bale group 3, it is a lengthwise arrangement. So, it is different now, and for this what if there are 2 bales I take, it is going to be L by 2, 1.7 is the length divided by 2, it is 0.85, and bale group 4 is again crosswise, so it is 0.8, so it is 0.8. So, these are the various width, and therefore, average bale width is going to be, overall average width is going to be summation of this divided by 4, because the 4 types of grouping and 4 types of arrangement. So, that gives you a value 0.74 meter. Therefore, total number of bales that can be accommodated is a lay down length is 34 m, 34 meter divided by 0.74. This means 45.9, that is roughly 46 bale we can accommodate in 34 meter length of the track which can be used. So, there are 46 bales we can accommodate, then bale group 1 we need 20% bale. So, actual number of bales is going to be 9.2. So, 9.2. Similarly, for bale group 2 the exact values 4.6, for bale group 3 it is 23, for bale group 4 is 9.2. So, obviously, base 9.2 cannot be taken, we have to go for integer value. So, 9.2 we can make it 9, this 9.2 also we can make it 9, bale group 3 23, this is integer figure. So, bale group 2 is 4.6, so we can make it 5, we can increase it, and the total will now come to 46. So, this is how we can find out that how many bales we can accommodate, and therefore, how many bales from each group we have to take. Okay. With this we close this session, and thanks.